Welcome to our presentation on igneous processes at continental arcs. This is a presentation for EOS 316 Igneous and Metamorphic Petrology in the fall of 2020 with Sean Marak and Curtis Knipp.
Hi!
We will be providing evidence from the volcanic rocks at the Central American Volcanic Arc.
The Central American Volcanic Arc is located where the Pacific Ocean meets Central America. Active volcanism is observed from the Guatemala-Mexico border through El Salvador, Honduras, Nicaragua, and down to Costa Rica. There is both fore and back arc volcanism, however we will be focusing on the rocks found in the forward arc in this case study. The arc is about 1,100 kilometers long. The axis shown above will provide the reference for those data analyzed. The CAVA is situated on an oceanic continental convergent margin. The Cocos Plate extends from the East Pacific Rise to its trench in the east along the Caribbean Plate.
The subducting Cocos Plate acts as a conveyor belt, providing hydrous minerals and enriched fluids beneath the overriding Caribbean Plate and fueling volcanism observed at the surface. In this study of the CAVA, we will look at the chemical composition of the igneous rocks found along the arc. Using trace elements found in the rocks, we will examine incompatible element compositions and isotropic evidence along the arc to identify tectonic controls for source mixing and melt extraction. Possible sources considered for the rocks observed at the surface include 1. Marine sediments, 2. Altered oceanic basalts, 3. Depleted mantle, 4. Enriched mantle, and 5. Continental crust.
Most of the data shown in the following charts for the CAVA geography and geochemistry is provided by the Rutgers University Central America Geochem database. Samples were collected from 39 volcanic centers across the arc over the last 45 years and compiled here. The highest peaks in the CAVA are located on the outermost margins of the arc, with the lower elevation volcanoes in the center. The thickest crust is located at the edges in Guatemala and Costa Rica, while the thinnest crust is located between El Salvador, Honduras, and Nicaragua. The correlation between volcano height and crustal thickness, if not obvious before, is presented here. Area isostasy is the first explanation which comes to mind when correlating thickness and height, but is there more than one reason? Farner and Lee showed in 2017 that around the world, higher volcanoes above thicker crusts are more differentiated with respect to magnesium, among other classic signatures, which in this setting is evidence for magmatic underplating and therefore crustal thickening.
The dip of the subducting plate is greatest at the center of the arc and at its shallowest at the margins. The variations in the volume of volcanic centers suggest complex structures in the overlying crust and varying past the surface. Age of the subducting slab at the trench increases steadily, about 20% from northwest to southeast.
Alright, let's get to the rocks. Looking at the composition of volcanic products, the majority spans the range of subalkaline igneous from basalt to andesite. There are a few dacite samples which were collected and even a few rhyolites.
Here is a ternary AFM plot of volcanic products. The volcanic products of the CAVA in general result in calc-alkaline trends, though sparse samples break through into the theolytic range. Now that we've identified the rocks, let's ask, how are these rocks formed and what evidence is there to back it up?
The range of the silica content is 45 to 75%, which covers basalt right through to rhyolite. This range varies across the length of the arc. This could be explained by multiple lava fields with multiple paths, as well as a plethora of magma batches with varying mingling at depth and along the path to the surface. Magnesium varies from being nearly completely foundered to over 15 weight%.
In 2000, Patino et alia showed how different incompatible trace elements could be resolved to distinguish a signal for the carbonate sediments. Observing enrichments in barium-thorium represents the hemipelagic sediments consistently, and uranium-lanthanum for the carbonates. Barium-lanthanum has little variation in the sediment section as well as high enrichment over the morb. This distribution makes barium-lanthanum the best tracer of slab signal for the sediment section as a whole. In 2005, Planck set thorium-lanthanum as a standard incompatible trace element signature of sediment recycling at subduction zones. He argued that they are less sensitive to assumptions about the prior state of mantle depletion. However, the observed thorium-lanthanum ratios in the rocks exceeded those found in bulk sediments. Planck went on further to hypothesize that the CAVA, Guatemala specifically, was anomalous because of the dominance of carbonates in the unit. Patino identified barium lanthanum as the strongest incompatible trace element ratio to predict the input of marine sediments to forming magmas. The orange line indicates the barium lanthanum ratio representing the bulk sedimentary contribution, determined to be uniform along the arc.
Just like how the barium-lanthanum ratio had been identified as the strongest incompatible trace element to predict the influx of sediments to a melt, the lanthanum-ytterbium ratio is established as an effective method of determining the degree of partial melt to occur in a rock, with lower ratios being associated with higher degrees of melting. In the CAVA data, due to the ratios observed, it can be determined that the highest degree of melting occurs roughly coincident with the steepest slab dips at around the 700-kilometer mark, and with the lowest degree of melting occurring near the end of the subduction zone where the dip is shallow. By the time Carr's 1990 study began, the usage of barium and lanthanum ratios to measure sediment input and lanthanum and ytterbium ratios to measure partial melting inputs were well established. By building on the works of those cited within his paper, he was able to build a mixing model between enriched and depleted mantle sources which explained trends observed. He did so through the investigation of the relationships between strontium and neodymium in order to isolate mantle sources.
Carr in 1990 showed that the neodymium isotope ratio can be used to determine the relative proportion of the melt that comes from the depleted mantle versus a more enriched mantle component. The neodymium isotope ratio correlates well with previously identified trends. Slab dip controls the degree of partial melting, which is captured by the sediment signatures and results in mixing ratio between the depleted mantle, enriched mantle, and members. Carr's cartoon illustrates the implication for the arc.
As the strontium ratio increases over time with the radioactive decay of rubidium, it can be used as a proxy for contributions from the continental crust. In the case of the CAVA, the oldest samples are located near the beginning of the subduction zone. This maximum age for the volcanoes at the start of the subduction zone is the reason for the increased silica content, as it points to an older, more felsic magmatic system. More felsic rocks seem to correlate well with the increasing strontium isotope ratios. When normalized by more values, the CAVA volcanic products exhibit a standard incompatible element behavior, namely enrichment of large ion lithophile elements. When overlaid with data from other locations, it becomes apparent that rare earth element content of the CAVA data matches within the ranges of other continental arc systems. The large ion lithophile content falls consistently average or just below average, though still well above the oceanic arcs for every large ion lithophile except cesium. Thorium is also in the lower end, which we attributed to a possible fractionation relative to lanthanum due to carbonate sediment input. When normalized volcanic product data is plotted with respect to volcanoes along the length of the subduction zone, a wide compositional range is observed, the largest disparity being between the Poas and Irazu volcanoes. Due to the similarities between the Poas volcano's product composition and that of the other volcanoes, and provided these results are typical for the Irazu center, it can be concluded that the rocks at Irazu are receiving a lower proportion of crustal and sediment inputs than the other volcanoes. This results in a comparatively lower incompatible element composition for the Irazu volcano. Other notable differences are apparent along the arc. However, due to time constraints, those will have to be explored at a later date.
How the basalts, andesites, dacites, and rhyolites found at the Central American volcanic arc are formed and why they display their particular geochemistries has been explored. The subducting Cocos plate consists of sediments with an identifiable signature along with the hydrothermally altered oceanic basalts, which are conveyed down under the overriding continental Caribbean plate. Dehydration of the minerals within the altered basalts, as well as fluids from the sediments, rise into the depleted mantle wedge. Depressing the solidus for the mantle wedge, it undergoes flux partial melting and carries with it a slab signature as its positive buoyancy carries it upwards. Meanwhile, circulation beneath the continent carries enriched mantle up and towards the wedge, causing decompression partial melting. This positive buoyancy is partially responsible for the heights of volcanoes, working in tandem with the formation of magma underplate. These sources underplate the continental lithosphere and through transfer of heat via conduction cause partial melting of the felsic continental crust. Eventually, positive buoyancy is returned and magma rises up through the continental crust, mingles a bit, and then forms stratovolcanoes, cinder cones, and lava domes, producing the variety of igneous rocks observed at the surface. Curtis and I would like to thank you for taking the time to explore the Central American volcanic arc with us today.